What another beautiful day we have here in AP Calculus AB. We have Arrow officially joining the team. We have now a team of 4. All right, so today's lesson, 1-5, IVT and EVT. Those stand for things on the back. You will see them, intermediate value theorem and extreme value theorem. They're two of the 3 that you definitely have to have memorized. So before I even jump into what those theorems are, I need to get some review on what it means to have symbolic notation on your graphs. So pretty straightforward. If I have an x-coordinate A, an x-coordinate C, and an x-coordinate B, then what is the height of these points? What are the x and y coordinates? So this one in red, I know it's black and white for yours, but in mine it's red. What are the x and y coordinates of this point? Well, what's the x coordinate? A. That might be -2. I don't know if these are scaled by 2. This is A. What is the height, the y coordinate of that point?
1.
F of A, assuming that this function is f of x, right? Let's assume that that function is f of x. Then it would be f of A. What about this brown point up here? What are the coordinates of that point?
C of F.
And f of C, there it is. Stega, what about this light blue point?
B.
F of B. All right, so we're okay with the notation. So if I were to say, what is this orange height right here? What is the number associated with that height? And again, you can't say 3 or 5. In symbols, what is this height? Someone? F of C. Right there is f of C. Someone else explain why. Well, that's where the height of this point is. Yeah, exactly. What about this point down here? What is this height?
F of A.
That's f of A. What about this height right here? Someone new. Arrow.
Wait, where?
This point,
Okay,
f of B, exactly. All right, so generally speaking, when we're talking about integrals, or sorry, yeah, go for it, Jay. Whenever we're talking about these theorems, usually we have some interval that we're talking about. Because remember, if you have a continuous function, it should be going from -infinity all the way to positive infinity. It's really hard to talk about so many numbers. So when we're talking about these theorems, we want to narrow it down to this window, some interval. Our interval is going to start from A, it's going to end at B. So generally speaking, this is going to be the left, and this is going to be the right. That is the interval that we're talking about. We don't care what happens over here at -infinity. We don't care what happens over here at positive infinity. We care about what happens in this window. Yeah, so you can't go through. Sorry. Do you need keys to get in there?
No, I think we can just.
You can go.
No,
You
yeah.
can just go.
Yeah.
There's a
Yeah.
desk block.
Well, we're gonna say bye because once you're like at a better stop.
Yeah.
Okay. So we only care about this window from A to B. So in this window from A to B, I'm looking for certain things. We don't know what things we're looking for because I haven't introduced the theorems. But now we know we're looking at the window. The other thing that I want to get a hold of is what it means to say this. So everyone write this down somewhere underneath here. What does it mean when I say f of C is greater than or equal to f of x? And I think Claire might know this from just calculus, maybe last time. If Arrow remembers EVT, she might remember this as well. What does this thing mean? It's gibberish. It's Chinese. It means symbols, Mr. Sindel. Go for it, Claire.
It means that point C is higher on the interval than X.
You're really, really close. Because x, in this case, is not a point.
Oh,
The
the
height.
point of C is either above or lies on the graph of Fx.
You're closer. Gio, what was the word that you used? You said h, height. Height needs to be in their definition. What this is saying is that the height of, and I guess I should label this, C is just some point that we picked. So I'm going to say this is some point. Maybe that some point was over here. Maybe it was over there. It's kind of a random point. In this case, it is a specific point, but it's just some point that we chose. So this is saying some height then. For some height is greater than or equal to. This is the important part, f of x. While f of x does mean the function, what it means in this context is all heights. So label it. This is all possible heights.
And it's just the X, right? Or is it the whole F?
f of x means all heights. X means all possible x coordinates, because that's what it actually represents. X is all x coordinates. That is x. F of x is all heights. That's another way to interpret it. So this is saying some height happens to be greater than or equal to all heights of the equation.
You want to do something I just remember? No, I'll stop.
After it is good. Okay, thank you. So what does it mean that one height is greater than all heights? Is there a word for that maybe starts with an M? Say it again. Maximum. That represents the maximum because some height is greater than or equal to all heights. The reason that we have to have that equal to is what happens if I have a constant function like this. Well then, yeah, there's the max right there, which is also right there, which is also right there. That is the max because it is greater than or equal to all of the heights. So
you're assuming this height is a longer function. It can't just be some random point that's not related.
yeah, so we're assuming that that is a specific point, not just one that we randomly chose. There exists some point that is a maximum.
Along the function.
Exactly, yeah. All right.
Just for this section where they're like local extremes.
There could be local extremes or there could be absolute extremes. Absolute is from negative infinity to positive infinity, the absolute extreme. But if we're just looking at a window, then we can say, well, there can be an absolute for the window or there can be a relative for the window. Exactly. We'll get into that more way later. You're way ahead of me. But yes. So, and of course, we have the second definition. I'm sure that people can get this. So let's go ahead and label it. This is a max. That is the definition of a maximum. Well, what is this thing? If I say some height, f of c, is less than or equal to f of x. That's a min. Exactly, Gio. That's a minimum because for some height, there's some height that is less than all the other points or equal to all the other heights. Some height is less than or equal to all of the other heights. That's what it means to be a minimum. Mathematically, we have made this more rigorous by applying these symbols to it. All right, so, oh, that's what that section was for. I was supposed to write it under there. Oh, well, we wrote it up there. I had it planned out, and I didn't follow the plan next year. All right, you want to write it again? Okay, go ahead and try to fold your paper down so you can't look at the notation. See if you can remember the notation for maximum. And if you get confused, go ahead and look up at the board. I will have it up here. Oh, I can't. Don't look, don't look, don't look, don't look at me. Don't look at me.
Did you make a teacher mistake?
No one caught it.
Oh.
I saw it. You say less or equal.
Arrow, Geo, log it.
I saw it too. I was when I said teacher mistake.
Log it, or log it, Claire. Arrow, I'll remember that you have one. I'll print one out for you. Oh, you do have one.
It's in here somewhere.
Log it now. Yeah.
How do you log it?
You've never logged it before. Just put the date in, like on the left-hand side, on the right-hand side, I'll do the signature. All right, let's go on to the types of intervals. I can get through this in about 30 seconds. Are we ready? Types of intervals. There's only two types of intervals that I know of, unless you like mix them and blend them together. But this type of interval, does anyone know it? What's the difference between these two? One of them has closed points, one of them has open points, so this is a what interval?
Inclusive.
Inclusive is a word you could use, yes, I agree. And it's actually a different word that we're going to use for this class, but inclusive is 100% correct. More mathematically correct in the United States would be, well, if they're closed points, closed interval. This is a closed interval.
I was like,
And these are open points, so this is an...
open interval.
there it is.
You're so smart.
Wow.
I just want you to know, if I say a closed interval, you can visualize what that is. You're like, okay, that means that the left endpoint and the right endpoint, those are actually like filled in dots. And if I say an open interval, you're like, okay, it doesn't matter what's happening at that point, but we know what happens in between there. So you can visualize what I'm talking about when I say these words. Good so far?
The open interval can have different types of stuff at the end. It doesn't have to be open.
Yeah. Exactly. So it just has to be some open point, which means I can't even do this. I'm not allowed to do that because that's now closed, because I do know what happens at that point.
It's a closed interval, even if that.
Is it
point filled by something
It's
else.
closed, but it's just a weird discontinuity at the end, so you usually won't ever encounter
And
weird
then
stuff like
if
that.
One closed point and one open point, it's still open, right?
That's a mixed, so I would call that open. Closed needs to have both of them closed.
Like
All right, let's flip over to the back. This is the important part of the lesson. Everything up to now has been review, even though I haven't really talked about maximum and minimum points in other classes. I have that solid definition, so we can use those definitions with our calculus theorems. And this isn't really a calculus theorem. I think I could probably teach this theorem in Algebra 1 and everyone would nod their heads and be like, yeah, duh. So when you think, yeah, duh, it's a simple theorem, I know. Okay, so here's the needs. Arrow, do you know the needs for this one? If f of x is,
0. Positive.
starts with a C.
Close. Continuous.
She does remember.
Oh my god. What the?
Continuous, write it down.
We need Aaron in this class more often. Oh, she's.
I've already done this. I've already taken this class. Oh, Jesus, Sean.
If f of x is continuous, so it needs to be continuous. That's the one condition. Other theorems will need other things. This only needs to be continuous. If we are continuous, then we know that f of x passes through all heights.
Okay.
This is a theorem that proves things about heights. Can we please all box the word heights? When we hit lesson 1-9, I'm going to say, what does IVT prove? And you'll be like, heights! Heights! It proves heights! It might be, you will be more specifically correct if you say that f of x passes through all heights between f of a and f of b at least, blah, blah, blah. You'll be more technically correct, but if you just use that one word, heights, IVT, needs continuous, prove height. That's all I want you to remember for your flashcard. IVT, needs continuous, prove height, you're done. You've memorized IVT. Of course, there's the more specific theorem, which is right here.
I have a question.
Yes.
On finals or like tests, are we allowed to use notes? Like every note?
Never, never, ever.
Because we have to prepare for it.
Yeah, if the AP exam let you use notes, I would let you use notes. I'm just following what AP does. So I'm really preparing you for it. All right, so it passes through all heights between f of a. What is f of a? Can we interpret f of a? That means height at a, height of a. This is a height.
Height of B.
Height of a and height of b. And even before I reveal the last word, height of a and height of b, that means height of a right there, height of b right there. Between those two heights, it passes
Once.
at least once.
Wow, Gio.
Good job,
Yeah,
Gio.
I'm just kidding.
At least
No, I
once.
didn't.
And that logically makes sense once we think about it more and more. But make sure that we really understand that. If we're continuous, if you have to hold down your pencil and not pick it up, and if you start at this height and you have to somehow end at that height, you have to pass through those heights at least once. Try it. I gave you two graphs. I gave you open and closed intervals. It doesn't matter the type of interval. See, we have this is f of a. This is the height at a. This is the height at b, f of b. I'm going to say, as long as you have to hold down your pencil, you're going to pass at least once through those heights. That means this height right here, this height is between f of a and f of b, so this height will be hit at least once. It might be hit thousands of times, but at least once, that's what the theorem states. Try it.
I'm trying to get to the other point, right?
Yeah. Try getting to this point, holding down your pencil, and not go through that height, which is in between f of a and f of b.
And we have to have
Just
it
go
be
over the.
And it has to be a function. It has to pass the vertical line test. You can't do something like this, because that's not a function. So if we have a function,
You have to pass between the two heights, right?
So you try to connect points A and points B.
yeah, connect this point and this point, holding down your pencil, that means it's continuous, and not pass through this height, which is between f of a and f of b.
Oh, so you don't have to pass it?
Try doing it so you don't pass it. See if you can break IVT. See if you can break the intermediate value
You
theorem.
can't do it.
You can't. That's because it's held true. Intermediate value theorem, it holds true. You're going to pass through them at least once. Can you pass through it twice?
No.
Yes.
Yeah.
And you
Ready?
go outside the map.
Woo, 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 woo.
You didn't pass it
Just
through
don't
twice?
look it up.
You haven't passed
This
it once?
this height right here was passed through 1, 2, 3, 4,
Oh, never
5,
mind.
6, 7, 8. Well, that's not really counting. It passed through it 8 times. It passed through it at least once, though, so IVT is held true.
So I could do as many schools.
You can do as many squiggle goals as you want, but the main thing to know here is that you will pass through all heights between f of a, between f of b, at least once, as long as it's continuous.
See, I knew that.
It can jump out of bounds. It can go way above f of b, and the theorem doesn't say anything. It doesn't say anything about these heights above f of b. It doesn't say anything about the heights below f of a, because you're not guaranteed to hit those heights. You are guaranteed to hit the heights between f of a and f of b. I think we can all probably nod our heads. I gave you 2 tries to do this if you want. You can do some other weird graph here. But yeah, you're always going to hit all heights between f of a and f of b. It doesn't matter if you're open interval. It doesn't matter if you're closed interval. You'll always hit that height. All right. Fist of 5, how are we following IVT? Does that make sense to us? 10. Oh, man, we're off the charts. All right. Extreme value theorem. All right. This needs 2 things. What 2 things do you guess they're going to need?
Open or close?
Open or close. One of those is correct.
Closed interval.
It's going to be a closed interval.
Yes, sir.
There it is. Arrow has the other one. It's continuous. So this one needs even more. It's a little bit more needy of a theorem. I need more. I need continuous and I need to be closed. Not just continuous. I need continuous and closed.
We're not differentiating yet.
Not yet. That's tomorrow. Tomorrow is a new theorem, which is a lot harder to think about. So I need a whole day to explain one theorem.
Monday, right? Not tomorrow.
Oh, Monday, yes.
There.
I was like, we're gonna have homework every day too. Oh god.
Okay, so if we have these 2 things, if it's continuous, if it's closed, again, closed, you should be thinking in your mind. Can you picture what closed looks like in your mind? What does closed look like? It looks like this. It looks like you have actual points at the beginning, at the end. That's what it means to be closed. If I have a closed interval, then
Close
it
on
proves
one
this.
side and open on the other side.
No, it has to be closed on both, yeah.
Does that make it open if it's closed on one side?
I would say it's not closed.
Very helpful.
That's the mathematician in me. Okay, so then this thing happens. Then this and this exist. What is this? What is this thing? We defined it earlier. This is a...
A maximum and a minimum.
Which one is it? What is this one? Right here.
Minimum.
That's the minimum. And this one is, therefore, the maximum. Thank you. Then that's all it says. So it proves that there is a min, there is a max. That seems like really easy. Like, well, there is a min, there is a max. How is it possible to not have a minimum, not have a max, right?
You can't.
There is a possible function that doesn't have any mins and max, but it has to break the fact that it's continuous. And it has to break the fact that it's closed, I believe. I'm thinking of the staircase to hell or whatever that function is called, where it is discontinuous everywhere. I'll show it to you later if I can look it up, but it's a really crazy function and it scares me because I still don't understand it. Later. Let's get through this. So we have continuous. You have to hold down your pencil. And it's closed, which means we start and end with a closed point. Try to make it so that there's no minimum and no maximum. Try it.
You
There's
can
no
just do like
possible way.
spirals.
Okay, it has to be a function.
Fast
And even with spirals, you do have a minimum and a maximum.
I suppose.
Try to do the line bending on the spiral.
Try it. Try something.
You can't.
Oh, darn. I have a maximum right there. I have a minimum right there.
I wonder
Actually,
if
the minimum is at this point.
the
Wait, you
equations
can't
for
have, like, a
your,
little-
graphs.
You have the minimum and the maximum if you.
Oh yeah.
Oh, I don't think I passed.
You have a minimum and a maximum.
Ooh, what if I just do a straight line? Will that break it?
You still have a minimum.
What if I just go like this?
There's infinite number of maximums.
There's an infinite number of maximums, infinite number of minimums. In fact, I've definitely proved the theorem by doing a straight line. Darn it! In fact, the minimum and the maximum are the same point, which is really weird.
For some reason, I was very confused on this. Both of these theorems, I couldn't understand at all.
Does it make more sense now?
I think
I explained it way differently last year. This, well, not way differently, but this makes a lot more sense.
There's more context now.
Yeah. All right, fist of 5. How well do we understand EVT?
5.
Okay, you're always going to have a minimum, always going to have a maximum. Can we please box min and max because we need continuous, need closed, and it proves that their min and max exists. All right, that's it.